Today we're going to learn Chapter 7, first order and a second order transient circuit. And for this class, we're only going to look at a first order transient circuit. The course objective is to analyze transient behavior of circuits. So the module objectives include the following: calculate the initial value for inductor current and capacitor voltages in transient circuit. Second is to determine the voltage and currents in first order transient circuits using differential equation method. And next is to determine the voltages and currents in first order transient circuits using step-by-step methods. So before we dive into the content of today's lecture, we're going to have a quick review about one important solution to a differential equation. So this is a differential equation, tau dy over dt plus y that is equal to f. And in this differential equation, y is a variable. Y is a function of a time t. And tau is a constant. And over here it's called a time constant. And f, that is a constant as well. From the other classes that you might have already learned how to solve the differential equation like this. That's not the focus for this class, but we're going to use the conclusion to that. The solution to this differential equation have a form of a y as a function of t that is equal to k1 plus k2 times e to the power of a negative t over tau for time that is greater than 0. k1 and k2 are two constants. They are related to the initial value and also the steady state value. And over here, k1 is equal to y at a time t is equal to infinity. And this is also called a steady state value that is also equal to f. So we can find it from this expression. From this expression, we know that if t goes to infinity, and this e to the power of negative infinity becomes 0, this term becomes 0, and it will leave us k1. And we can also find it from over here. For t that is equal to infinity, means in steady state, dy over dt that is equal to 0, means y at a time t is equal to infinity, which is equal to f. This is how we get a k1 is equal to f. And the initial condition, if we submit a t that is equal to 0 plus means t at a time right after 0. So that is represented as a 0 plus. At a t that is equal to 0 plus, and then we put a t is equal to 0 over there, and this is e to the power of negative 0. So that is 1. So yt at a time 0 plus is equal to k1 plus k2. So that is how we get a k1 plus k2 is equal to the initial condition. So this is the conclusion that we're going to use for the rest of today's lecture. Let's first take a look at a charging and a discharging circuit. And over here we have a circuit with a power source Vs and a resistor Rs. And this is a capacitor with a capacitance of C. And the voltage on this capacitor is Vc, and this is a function of a time t. Initially, we have the switch connected to the left-hand side. It means this is a charging phase, and the Vc will increase. So this represents the phase like from here to here. After a long time, when it's fully charged, and we know the voltage Vc will be equal to Vs when it's fully charged, right? Because when it's fully charged, this will be modeled as open circuit. The open circuit, the voltage Vc between this node and this node, that will be the same as a Vs. If we flip this switch to the right hand side, it will start discharge. We will have a current running through this resistor R, and over time the voltage of Vc will drop, which represents the phase from here to there, and eventually goes to 0 when all the electricity is consumed. And this charging circuit looks like this. We're going to look at a charging phase and a discharging phase separately. For the charging phase, when we have the circuit switched on, and initially assume that Vct is equal to 0 initially. When it's switched on, and we can use the KCL and KVL to do analysis for this circuit. And the way to do analysis is exactly the same. The only difference is at the place when we calculate the current going through a capacitor or the voltage on an inductor. So that is the only difference compared to what we have learned from the previous chapters. All right, if we apply KCL at this node A, so this is our node A. Apply KCL at this node. The current goes into this node is equal to the current leaving the node, or you can say the current leaving the node adds up to 0. So that is how we wrote this equation. The current leaving this node through this capacitor, which can be calculated by using C dV over dt. And the current leaving this node from this resistor RS, that is equal to, if we select this node as reference node, as a reference node, this node will have a nodal voltage of Vc, and this node will have nodal voltage of Vs. So that will be Vc minus Vs divided by Rs, which is equal to 0. So this is how we write the KCL equation. And we can reorganize this a little bit to give us a standard form. So the variable over here we care about is Vc, which is the voltage on this capacitor. This will be the variable y in the conclusion that we brought up in the first page. And we put a y over here, Vc. We multiply Rs on both sides. So the equation on the left-hand side becomes Rs times C times dVc over dt. And over here we have Vc over Rs times Rs, which gives us Vc. And we put the constant Vs to the right-hand side. This is a standard form that we have. Once we know this standard form, we know that the time constant tau will be Rs times C. So this is our time constant, right? At the same time, the solution will be of this form. So Vt, that is equal to K1 plus K2 times e to the power of negative t over tau. And we also know that K1 is equal to the steady state value, which is equal to the constant on the right-hand side. So we know K1 is equal to Vs. At the same time, K1 plus K2 is equal to the initial condition y at t 0 plus. So K1 plus K2, that is equal to Vc at time t is equal to 0 plus. And we assume that it starts from 0, and this will be 0. So K1 is equal to Vs, K1 plus K2 is equal to 0. We can find K2 is equal to negative Vs. So that's how we can find the final conclusion Vc, that is equal to K1, which is Vs, plus K2, K2 is equal to negative Vs, times e to the power of negative t over tau. And over here, tau, that is a time constant, which is a Rc. So that is how we solve this problem. So this is called a transient behavior. Discharging phase will start with a Vc fully charged. Then we flip the switch to the right-hand side, and we'll connect this resistor to the circuit. And we know that Vc starts from a value of a fully charged value. That's called a Vc at the time 0. So over here, the time 0 is different from the previous time 0. So right now, time 0 starts from the time that we start to turn the switch on. So again, we can write the KVL equation for this loop. If we write a KVL equation, we'll count the voltage drop of this loop. This is single loop, right? The voltage drop on this loop adds up to 0. So voltage drop on this resistor R, that is equal to R times the current. The current through this network, that is equal to C times dV over dt. So this is the voltage drop on this resistor. The voltage drop on the Vc, that is minus Vc, that is equal to 0. So this is the equation that we have. By comparing this equation to the conclusion that we got from the first page, we know that the time constant tau is equal to Rc, and the steady state value is equal to 0. So we know that K1 is equal to 0. Initial condition K1 plus K2, which is equal to Vc at time 0, and we said it's equal to Vc 0. And we know that K2 is equal to Vc 0. So this is how we find the conclusion Vc of time, Vc as a function of t, that is equal to Vc 0 times e to the power of negative t over tau. Since we are looking at this phase from time that is greater than 0, so for this conclusion, it works for time t that is greater than 0. And time t is equal to 0 is something that we selected. We select a time period that we are interested in, and we can select, that's how we select time t is equal to 0. All right, now we finished the basics about the charging and discharging transient circuit. Let's look at one more complex example. So we have a problem over here. This is a capacitor circuit. We have a capacitor is a 100 μF. This is a power source, and at time t is equal to 0, we're gonna open the switch, and we want to find out what of this output VO is from over here. For transient circuit, something of our interest from the beginning is the voltage on the capacitor or the current through an inductor. So that is something that we need to figure out. If we can figure out a VC, and in this problem we can find VO. VO is a part of VC by using the voltage division circuit, right? So this is the voltage applied on these two resistors. We are looking for the voltage on one resistor. So now the problem becomes how to find a VC. To find a VC, there is a governing equation. Now this governing equation is a differential equation. We can find this differential equation using the KCL or KVL. So if you use a KCL, there are not many nodes. If you use a KVL, and there is this one loop. So over here, there's not a big difference. So if we use a KCL, choose this node as reference node, the current goes into this node will be equal to C times dVC over dt, right? Which is the current goes into this node. And the current goes into this node from the second branch, from this branch, which will be equal to the voltage VC divided by the resistor R1 plus R2. So this is how we get this equation. After we get this equation, everything becomes very straightforward. We put this into a standard form first. To put the standard form requires us to have a constant tau times dVC dt plus Vc that is equal to some constant. So that will be our standard form, right? So after we put this into this standard form, we can find our time constant tau, which is equal to R1 plus R2 times C. And K1 is equal to the constant on the right hand side, which is equal to 0. K1 plus K2, which is the initial condition, which is Vc at t that is equal to 0. So over here, I want to point out that how to find the initial condition. So we haven't talked too much about how we find the initial condition. So this will use the continuity property for capacitors and inductors. For capacitors, the voltage on this capacitor is continuous. So we are looking for the voltage at t is equal to 0 plus. This will be equal to the voltage Vc at t is equal to 0 minus, because it's continuous, right? So we're going to use the continuity property. So Vc at t that is equal to 0 minus will be found from a different circuit. Because the circuit at t is equal to 0 minus, this is not open, this is closed. So we're looking at this full circuit. So the voltage over here is in steady state. Before it comes to t0, this circuit has already been in that situation for a long time. That is another steady state before we switch the switch. So in that case, this will be modeled as an open circuit. The voltage on this can be calculated by using the voltage divider. The total voltage is equal to 12 volts, and the voltage drop on these two resistors that is equal to 4 plus 2 over the total resistance, which is 4 plus 2 divided by 4 plus 2 plus 3 times 12. The initial condition that is equal to K1 plus K2, and with K1 is equal to 0, we'll be able to find a K2. So after we find a K1, K2, and time constant tau, we'll be able to find the conclusion. So that is equal to K1 plus K2 times e to the power of negative t over tau. So this is how we solve this problem. Let's look at another example with the inductor. So this circuit has an inductor. Before time 0, the circuit is open. At time is equal to 0, the switch will be pushed following this arrow. So it will be connected. Before 0, this circuit is an open circuit. So the current through this inductor is equal to 0. And once we switch this on, the initial current for L, if we look at it, the turn at the time t is equal to 0 plus, that is also equal to 0 because of the continuity property for inductors. The voltage for capacitor that is continuous, the current for inductor that is continuous. So this is the continuity property that you need to remember. So the same thing, the first step, we're going to find the differential equation. The differential equation is already defined by looking at t that is greater than 0, because that is something we're interested in, right? So after this circuit is put on, and we can find the differential equation by using either KCL or KVL. If we write the KVL equation, we'll count the voltage drop, right? The first voltage drop, which is the VR. The second voltage drop will be L times di over dt. The third voltage drop, which is negative Vs. So that is how we find the equation, right? So we'll use the KVL to write this equation. The voltage drop on this resistor, which is equal to VR. VR can be calculated by using the current IT times R. And the voltage drop on this inductor, which is equal to L times dr di dt. And the voltage drop on this component is equal to negative Vs. So we have negative Vs is equal to 0. So this is the KVL equation. So after we get this KVL equation, we can put it into a standard form. And this is a standard form. And we divided the equation by R on both sides. So we have L over R here. And this will be I. And on the right hand side, it will be Vs over R. So this is how we get the differential equation. After we get the differential equation, the rest is to find these constants. IT that is equal to K1 plus K2 times e to the power of negative t over tau. So K1 is equal to the steady state value I at a time that is equal to infinity. At time is equal to infinity means this has been closed for a long time. What will be the current? So after a long time, in steady state, this inductor will be modeled as a wire. So the current will be equal to Vs divided by R. So that is how we find the steady state value, and it's also equal to K1. And the initial condition is the current at a time t that is equal to 0 plus. At t is equal to 0 plus, and this will be found by using the continuity property, which is equal to the current at a t that is equal to 0 minus. At a t is equal to 0 minus, when this is off, and we know this is equal to 0. And that is equal to K1 plus K2. And since we already got K1 from the previous equation, and we'll be able to solve for K2. So that's how we solve the differential equation, and we find the final answer IT is equal to Vs over R times 1 minus e to the power of negative t over tau. And remember tau over here, that is equal to L over R. Now you see some fundamental equations that we have obtained. For circuits with an inductor, the time constant is always equal to L over R. And for the circuit with a capacitor, the time constant is always equal to R times C. And we already know C, but what is this R? And for the simple circuit like this, R is the total resistance of this network. And similarly, for here, and this R is the total resistance of this network after time for t that is greater than 0, right? And we also know that from what we learned from chapter 5, the Thevenin equivalent circuit, for any circuit, we can find it's a Thevenin equivalent circuit. If we take this capacitor or inductor out, and we put the rest of the circuit to be it's a Thevenin equivalent, and in that circuit there is only one resistor. We know that this R has to be equal to that resistance. A resistor has to be equal to the resistance of that resistor, right? So that is something that we, if we combine the knowledge we learned from previous chapters, we have some conclusion. This R is equal to, it's a Thevenin equivalent, is equal to the resistance of its Thevenin equivalent circuit. So that is some conclusion that we got. Now let's look at a more complex problem with one inductor in the network. In this problem, we are looking for VO. VO is over here, the voltage on this 2 ohm resistor, and there's one inductor over here. We need to find out what happened to this inductor before we can find out what is the VO. If we know the current through this inductor, the VO can be easily calculated by using the current times the resistance 2 ohm, right? So now the problem becomes to find the current going through this inductor. So the first step to find the differential equation for time t that is greater than 0. And this is also called the method, this is also called the differential equation method. So from the very beginning of the slides, we learned the module objectives, right? The second objective is to use differential equation method to perform a circuit analysis. So this method is called a differential equation method. So the first step to find a differential equation. So the differential equation will be obtained at a t that is greater than 0. When t is greater than 0, this is open. So that circuit is a single loop circuit, right? This is a single loop circuit. And we can write the differential equation by using KVL. We count the voltage drop of this whole loop as up to 0. If we start from the voltage Vs over here, then we follow the direction that I drew over here. This is the loop that we are following to write the KVL equation. So we have negative Vs, then plus the current, which is the same current I, let's call it IT, I times R1 plus voltage drop on this inductor, which is L di dt, plus voltage drop on this R3 resistor, which is equal to I times R3, that is equal to 0. So this is how we get the differential equation. After we get this initial form, we are going to put this into a standard form. The standard form requires some constant time derivative of a variable plus this variable that is equal to some constant. And we know this is equal to K1, so we already find K1 is equal to 6, right? And the second part is to use the initial condition to find K2. So initial condition V at the time t is equal to 0 is equal to K1 plus K2. You have two different options over here. You can either write this the differential equation in terms of something we are looking for eventually, or you can write the differential equation by using the current going through this inductor. So what I wrote over here, that is one choice, that we write the differential equation in terms of VO, because VO is equal to I times 2. So we can simply write this in VO. If we write a VO over here, we are going to use VO at a time t that is equal to 0 plus. And if we use the current I, and over here initial condition becomes I at a t is equal to 0 plus. The two different options are more or less the same. So from over here, we can find a K1, find a K2 from the initial condition. Then we'll be able to find the final conclusion, V that is equal to K1 plus K2 times e to the power negative t over tau for time t greater than 0. Next, so we mentioned this briefly already about how do you calculate time constant. So from the examples, we know that for a circuit with one capacitor and a time constant that is equal to C times R, and this R is a Thevenin equivalent resistance. And for a circuit with one inductor, the time constant that is already equal to L over R, and this is the same. R is equal to, it's a Thevenin equivalent resistance. That is obtained by simplify the rest of the circuit other than this inductor or capacitor. So we replace this whole part by using its Thevenin equivalent circuit, which have a voltage source VTH and a resistor RTH. Then we put this inductor or capacitor back into the circuit for analysis. For a circuit with one capacitor, we can write this differential equation by using KVL. So the voltage drop on this resistor RTH, that is equal to RTH times the current. The current is equal to C dV dt, plus the voltage drop on this capacitor, which is VC, that is equal to VTH. So this is how we find the time constant tau is equal to C times RTH. And similarly, if we put this inductor into the network, the same thing, we can write the differential equation by using KVL, and we find this. The time constant tau is equal to L over RTH. And something else we can find from the circuit is the steady state value, which is also K1. K1 is equal to VTH because K1 is equal to something on this right hand side, right? For a circuit with the inductor, the K1 is equal to ISC, which is also equal to VTH over RTH, because we are looking for current over here, right? So if we look for the current through an inductor, the steady state value is equal to VTH over RTH, which is also equal to ISC. All right, so we summarize all the conclusions that we need to know about this topic. Let's look at one example. At a t is equal to 0, we're going to put a switch on. And we can find a Thevenin equivalent circuit for the rest of the network without considering this capacitor. So we take this off, now we look at the rest of the circuit, we will find it's a Thevenin equivalent. To find a Thevenin equivalence, we already learned everything about that from chapter 5, so I'm not going to repeat. So I would assume that you can find it's a Thevenin equivalent circuit. So after we find a Thevenin equivalent circuit, we find a VTH and RTH. Given it's a Thevenin equivalent circuit with this voltage source, this resistor in series with one capacitor, we can find the Thevenin equivalent circuit. We can find it's a differential equation related to this equivalent circuit that gives us RTH times C times dV over dt plus Vc that is equal to VTH, and time constant tau that is equal to RTH times C, and K1 is equal to VTH, and we can solve K2 from its initial condition K1 plus K2 that is equal to Vc at time t that is equal to 0. Vc at a time t is equal to 0 plus is equal to Vc at a time is equal to 0 minus, and Vc at a t is equal to 0 minus is get from this circuit before it's switched on. Before it's switched on, we have this circuit and we have open circuit over here, and the voltage on this capacitor is equal to the voltage drop on this resistor, which is half of 12 volts, which is 6 volts. That's how we solve for K2. After we get a K1, K2, and a time constant tau, we find the final answer. So from the calculation, we find IOT that is equal to 1 milliamp. Current IOT is over here. So it means that when you flip the circuit on, there is no change to the current going through this branch.